2014 Level 2 Waves Paper Question 3. Watching the waves. Myan is watching water waves coming into the beach. She estimates the wave speed to be half a metre a second and the wavelength to be 1.2 metres long. Calculate the frequency of the waves and give your answer with the correct unit and the correct number of significant figures. I'm going to deal with units and significant figures now. Unit, its frequency should be hertz or per second, second to the minus 1. Significant figures. We have V equals F lambda. We're trying to find the frequency, so it's going to be F equals lambda over V. We're given the wavelength, so that's lambda. We're given the estimate of the speed, and so we're just going to use that formula. Those are the two things we're multiplying and dividing. So our rule is multiplying and dividing. We use the same number of significant figures as in the raw data. So it's going to be to 2SF. With the unit of hertz is better than seconds to the minus 1, just because it's more commonly used as far as I know. Okay, so that's a simple question, unless I've done something obviously wrong, but I don't think I have. B, at another place there are two gaps labelled S1 and S2, as you can see from the diagram there, S1, S2. In the line of rocks, there's a set of waves passing through the gaps, creating an interference pattern. Okay, as soon as you read two gaps, you should be thinking 2-point source interference. That means two sources which are at a point, and it's the interference pattern for them. Okay. Difference between the distances from S1 to X and S2 to X. Actually, I had my mind the wrong way. The waves are going up that way and interfering on the other side. That makes sense. So the difference between the distances from S1 to X and S2 to X is 0.40 metres. What is that? That's the path difference. Path difference, PD, that's path difference between 2 metres and 1.6 metres. The speed of the wave is that, and one wave reaches the wall every second. So that gives us a frequency also of 1 hertz, 1 per second. And we've got our V, in case that comes up. Is the point at X a node or an antinode? Explain your answer. So first of all, you need to know what a node is. A node is a point of 0 amplitude due to destructive interference. Okay, the destructive interference comes about because a crest is meeting a trough and they cancel each other out. Okay, so one's high and one's low and they add up to be nothing in the middle. So that occurs when, so we're actually doing the whole explanation, but now that occurs when there's a half wavelength path difference. So we have to work out what the wavelength is and what the path difference of that is. Okay, so do we have the wavelength? Can we use the wavelength from above? Let's just go and have a look. I think it's a different situation. No, water waves, the wavelength is 1.2 metres. So I think it would be fair to use that 1.2 metres. No, I think it's a different situation now. We can't use that. Okay, the reason why is the wave speed is 0.80 metres per second. So in 1 second it travels 0.80 metres, but we've also been given the information that one wave reaches the wall every second. So one wave per second, it's frequency of 1 hertz. The wavelength, we have to use V equals F lambda again. This time rearrange for lambda equals, VF. The velocity was 0.8, and our frequency is 1 per second, so our wavelength is 0.8 metres. Okay, so a different situation. Could have got it wrong if we didn't read the question, think about it carefully. Okay, so 0.8 metres for a full wavelength. Is that half a wavelength path difference? Well, 0.40 is half a wavelength path difference. So you're going to get in fact, if we were to look at this really carefully, we would see there are 2 wavelengths in the 1.6 metres, and there's 2.5 wavelengths in the 2.0 metres. Half wavelength path difference to X, we're going to cancel out, and we're going to be a node. Okay, so antinode, we didn't quite get to that, but antinode is when there's constructive interference, a peak meeting a peak or a trough meeting a trough. Okay, all of that information that I described, if you boil it down to some key bullet points and write that in there, you'll get excellence for that question, I imagine. C. Moana watches the waves travel from deep to shallow water. Okay, so from deep to shallow water, that's right to left in this case. You can see the arrows going that way. I always think left to right. So when they're doing that, going right to left, they're usually, I think most people think left to right as well. So when they're going right to left, they're trying to trick you just a little bit. Okay. Complete the diagram showing the wave fronts and the wave direction in the shallow water. Easier to start with the wave direction. So deep water, the speed of the waves is higher. Shallow water, it's much harder to move. There's less of a medium there. It has to push them up. So it's harder and harder for the wave to travel at speed. So that means high to low speed, it's going to bend towards the normal. Okay, so we're going to get a bending in this direction. And that means the wave fronts are always perpendicular to that direction of wave travel. So that's going to have to bend around to do the same thing. And you should have a smaller, does that make sense? Yeah, smaller wavelength. And that means the wave fronts will be closer together. And the bending is in that direction. Yep, that's pretty much it. And it makes sense. When you have big long swells coming into shallower water, the waves start to break and catch up to each other as they get closer together. Okay, D. At school, Moana investigates waves and springs. Okay, springs a little bit different. She connects a light spring to a heavy spring and ties the heavy spring to the leg of a bench. You can see the top view given just here. Moana sends a single pulse along the light spring as shown in the diagram below. Waves travel faster, this is nice to know, waves travel faster in a light spring than in a heavy spring. So fast and light and slow and heavy. Okay, presumably the heavy spring takes more energy to move, it's harder to get, anyway, okay. The diagram below shows the pulse after it's moved into the heavy spring. On the same diagram, draw the pulse reflected in the light spring, showing the phase of the pulse. Okay, the phase is going to be underneath, so it's going to be an underneath kind of 180 degree phase difference. Okay, and the distance travelled by the pulse, if it's faster, then this distance, 1, is going to be larger. See, notice I've gone to the peak of each. That distance, 1, is going to be larger than distance, so I haven't drawn it very well here, so it might be somewhere down here. But D1 is going to be larger than D2. That's because it travels faster in the heavy spring. Giving reasons for your answer. I've explained why the distance will be larger, because it's a faster wave speed. The reason why you get the phase change is on reflection there's just a rule here, but on reflection to a heavy boundary or a more dense or a slower medium or a higher refractive index might be better, then you're going to get that 180 degrees phase change. One thing the question hasn't asked you to do, but a future question could, is to draw the respective amplitudes as well. So you would have overall the amplitude here plus the amplitude here shouldn't be greater than the amplitude here. The amplitude contains the amount of total energy, so there should be less total energy in each, less in each of the individual ones than in the original total. But you can think about that more. We'll leave it at that. Okay, all the best for your exam this year.